impedances are different. Remember, bone is going to have a high rate of impedance, right? It's going to be very resistant to sound. Remember, it's going to absorb and scatter a lot of that sound, right? Soft tissue, we know it's going to travel. Okay? Just like, or soft tissue and air. Those are kind of opposite, because air is on the opposite end of that spectrum, right? You're going to get a lot of scattering, right? A lot of scattering there. Think about the lungs. You get a lot of scattering with the lungs. Soft tissue, it travels well through soft tissue. So the greater the impedance, the greater the reflection is going to come back. Okay, so we have a soft tissue to fat interface. Yeah, we're going to get a reflection, but it won't be an intense reflection, just because their impedances are very similar. Okay? Remember, impedance has to deal with the resistance to sound traveling in that medium. Okay. And I'm gonna come to that. I really started early. I shouldn't even said that right then, because I hit it kind of early. I'm excited. Okay. The intensity transmission coefficient is the percentage of the intensity that travels in the forward direction when the beam hits the interface between two medium. Okay. That's just the percentage of the beam that's being transmitted. That's the intensity transmission coefficient. The percentage of the beam that's being reflected, that's the intensity reflection coefficient. Okay? I have a long definition, but I'm telling you. The percentage of the beam that's being transmitted, ITC, percentage of the beam that's being reflected, IRC. In clinical imaging, 99% more of the sound wave's intensity is transmitted at the boundary between two soft tissues. Okay? Be careful when we ask these questions, guys, because if I ask you something about an intensity reflection coefficient or intensity transmission coefficient, that means I need to have that number in a percentage, right? If I'm asking you about intensity, you can just give me the number and with the watts per centimeter squared, right? So be careful when you're reading the questions, okay? If I'm talking about coefficients, ITC, IRC, I need that number in a percentage. Okay? Intensity, I need that number in the correct units. Remember, percentages, they're dimensionless. They're unitless numbers. Okay? A smaller percentage of the wave is transmitted when the sound strikes a boundary between bone and soft tissue. Yes, I do. And that's true because we know that that bone is gonna absorb a lot of the sound. All right, that's why it's not a lot of wave. Or just think of like think of a stone, right? Remember I said that it's gonna absorb a lot of the sound, which is why you get that shadowing behind it, right? Because the sound can't penetrate that. It's not gonna be able to go through it. Okay, because we're talking about transmission right now. Okay, the sound's not gonna be able to go through it.
Shadowing.
So why is it black?
Because if no sound penetrating, you can't get a returning echo back.
Oh, okay, that's right.
You're not gonna get a returning echo back. That's why it's black.
So because it's solid, you get the shadow?
Yeah, because the stone is absorbing that sound. So anything posterior to that stone is you're not gonna see any of that anatomy, because the sound is not getting there unless you change your angle and hit it at an oblique angle. Then you can see past that stone. Right? But if you're perpendicular to the stone, anything that's in the line perpendicular to the stone, you won't see past it. Okay, because that stone is going to be the same thing with bone. You can't see past bone, right? Think about those ribs, how they're always in the way, right? They always call that black line on your screen,
right? Black
streak. That's because you're getting hit in the anterior part of the near field, and everything posterior to that is going to be black because the rib is absorbed all of that sound.
Why do other images bone shows up as white?
That's the reflection, because that's the difference in impedance between the soft tissue and the bone. You're gonna get that. Yeah, you're gonna get the most anterior reflection, just like you see the stone, right? You always see that anterior reflection of the stone, but you don't see the whole shape of the stone, right? So you're gonna see the initial, the most proximal part of the stone, or the stone that's most superficial, or the part of the bone that's most superficial. That's why you can see the outline of the bone, but you can't see the whole shape, right? Because it's not going to be able to penetrate that to give you a reflection back.
So is the shadowing artifact is same as posterior enhancement?
Definitely not. The posterior enhancement is because the sound is able to transmit.
Okay.
It's not being impeded.
Okay.
It's not being impeded at all, so it's able to transmit. So it's transmitted actually easier. That's why you're getting that enhancement.
Okay.
Like in the fluid, in something that's fluid field, the bladder, the gallbladder.
Mm-hmm.
Start paying attention, guys. When you're looking at your gallbladder, you'll see that posterior enhancement on that gallbladder. Okay. It's not. It won't be just as bright as like when you look at the bladder. The bladder, you see it very well. You look at, you have a cyst, you see it very well.
Mm-hmm.
Okay. Main thing I want you to remember: less than 1% of the beam intensity is being reflected. Okay.
I see.
99% or more of the beam is being transmitted.
TC.
Okay. So the coefficients, because they're percentages, like I said, they're dimensionless. But if we add the IRC plus the ITC, we should get the
100%.
initial intensity. Okay, of 100%. It should always be 100%. Guys, look at those questions at the end of that chapter, or end of that little section. Answer those questions, okay? Be sure to do that this weekend. Question in the back of the book, guys. Question in the middle of the chapter, guys. I'm saying it again. Do you got me on record?
Yeah.
Question in the back of the book, guys. The question at the middle of the chapter. Okay, as sound breeze strikes a boundary, energy is conserved, and 100% of the intensity must be accounted for. Remember, intensity, we're talking about energy there. So again, we don't lose energy, right? Energy just transforms to another form of energy. So as far as the initial intensity, it has to be accounted for than being 100%. So again, if I'm asking you about the ITC, the IRC, those are percentages. Okay? Both of those must equal 100%. Okay?
In every angle or just in
Every
right?
angle. Every angle. No matter the angle. Alright? So let's do a little quick review. At the boundary between two medium, this is all about incidence up until this point, guys. The principle of conservation of energy applies, right? Because we don't lose energy, it just transfers from one form to another. Okay? If the reflected and transmitted intensities are added, the result must be the incident intensity. Okay? Mind you, we're talking about intensity right here, right, guys? That's not saying that has to be 100%. If my incident intensity is 50, and my reflected and transmitted are 25 apiece, that's fine, right? Because they don't have to be 100%. They're not percentages. They're intensities.
Okay.
Okay. So when we talk about the reflection coefficient and the transmission coefficient, when they're added, those are percentages. They must equal 100% between those two. Okay. That's why I'll keep repeating that, because I don't want you guys to be confused. I don't want you guys to miss that. I want you to know when we're talking about coefficients, we're talking about percentages.
Right.
It must equal 100%. Okay. We're talking about intensities. They don't have to equal 100%. Do they have a question? They do have a little question in there, right? I want to do one real quick. I don't want to move past this real quick. All right, guys. Let's go to page 94. Page 94. I'm just going to do one real quick. Page 94 states, question number 1. If you don't mind, can you cover up your answer with your hand, right hand? Cover up your hand. Okay, I'm going to read the question. A sound wave with an intensity of 50 watts per centimeter squared strikes a boundary and is totally reflected. What is the intensity reflection coefficient?
100%.
No, 50.
It's actually for a coefficient, right? It's actually for a coefficient, right? So we know that our answer choice should be in percentage.
100.
100%.
Oh,
It's telling you that it's totally reflected.
I read it.
It's totally reflected. That means none of that beam was transmitted. So that means our ITC is 0%.
Right.
Okay?
ITC? Oh,
Yeah, because it has to be accounted for. They have to equal 100%. It's telling you right there that beam. That's what I'm saying. Don't get thrown off by the numbers. So let's do the next one. The next one is just the opposite way. A sound wave with an intensity of 50 watts per centimeter squared strikes a boundary and is totally reflected. What is the reflected intensity?
50.
50 watts per centimeter squared, right?
Yep.
Right? So I don't want you guys to get confused between intensity and coefficients. Are we good there, guys? We understand those questions? Why they're different? Adelaide? We're good there? No? Okay, like I said, so the first question is really, you can really don't even have to worry about the 50 watts per. It's telling you already that it's being totally reflected, and it's actually for a coefficient. So totally reflected means 100%, right? All of it. Okay. So it's actually what is the intensity reflection coefficient? If it's telling you it's totally reflected, that means our IRC is going to be 100% because all of that sound from the incident intensity got reflected back. Okay. Okay. You gotta pay attention to what they're asking you for.
Okay, number 2 is still the same, totally reflective.
It's actually for what is the reflected intensity. Underline those words. Underline those words, guys. It's actually what is the reflected intensity. This is actually what is the intensity reflection coefficient. Okay? Be careful. I'm telling you guys that for a reason. Alright? We're good? We're good there? If not, I'll get with you guys after class. Okay? Okay. So, real quick, before I even move on past that part, because now we're about to get into, reflections with normal incidence, and we're going to talk about incidence the rest of the way. Okay, we're good, guys, on our IRC, ITC, incidence, oblique incidence, normal incidence, synonyms, orthogonal, 90 degrees, right angles, perpendicular. You good with those, Myra? Okay. So if you're taking notes, this is where you draw a line. So now we're about to go into another little subject. All right. All right. So let's talk about reflection with normal incidence. Reflection with normal incidence. What does that mean, Pat? What does reflection with normal incidence mean?
90 degrees, reflected back 90 degrees.
Dang, our initial intensity is hitting the barrier at 90 degrees. Okay, it's hitting that perpendicular to that part of anatomy. Okay, here's our anatomy right here. Our medium. These are 2 mediums. This is our boundary right there. It's perfectly hitting that boundary at 90 degrees or perpendicular to that boundary. That's what we're talking about. So we're going to talk about reflection with normal incidence. So we just concentrate on this reflected wave. Don't worry about this transmitted wave, because remember I told you that's when we talk about transmission, we're usually referring to the law of conservation of energy. Whatever part of the beam that that's not reflected has to be transmitted. Okay? Isn't most of our beam transmitted though? More than 99%?
Mm-hmm.
Okay? I'm just telling you guys different ways. Okay? So this, when a sound beam strikes a tissue boundary at a 90-degree angle, that's normal incidence, of course. Reflection occurs if the media on either side of the boundary have different impedances. Okay? So if we're going from soft tissue to soft tissue, we may not get a reflection, right? So that's why as we're traveling, it has to be a different impedance or a different resistance to sound for us to get a reflection on that boundary. Okay? So if this is going from medium 1, soft tissue to soft tissue, we're not going to get a reflection. That sound is going to keep transmitting. But if this is going soft tissue to bone, remember I said this earlier? Soft tissue to bone, remember, soft tissue doesn't have a high impedance number. It's not highly resistant. Okay? But that bone is, right? That bone is high, so that's gonna have us create a big strong reflection. The impedance, when we're talking about normal incidence, the impedance is difference between the 2 mediums. That's what gives us a reflection. Okay? The bigger the impedance difference, the bigger the reflection we're gonna get. Okay? If the impedance difference are very similar, we're not going to get much of a reflected sound beam. Okay? A lot of that sound is going to keep transmitting. All right. So the percentage of the incident beam that is reflected is related to the difference in impedances of the tissue, like I just said. Okay. So we will not get a reflection, and I got it in red, yellow, and green, guys. So red means stop. No. All right. We will not get a reflection if the 2 media have identical impedances. Okay, if we're traveling from, soft tissue to soft tissue, fat to fat, we're not going to get a reflection.
Oh.
Okay, all right. We're going to get a small reflection will occur if the impedances are slightly different. Soft tissue to fat, we're going to get a small reflection if they're slightly different. Okay, we're going to get a great big nice reflection when the impedances are substantially different, when they have a vast difference in impedance values. we're gonna get a nice big reflection. Okay, mind you, this is just with normal incidence right here. We're hitting the structure at 90 degrees. We're hitting the structure orthogonally. We're hitting the structure perpendicular. Okay, or at right angles.
If the medium more concentrated, intensity, no, density, more density or less density.
Talking about impedance, the resistance, not density. Remember that has to do with propagation speed. We're talking about impedance right now. The resistance it has to sound travel.